MathemAddicts at Custis River College in Sacramento, California. This is a video lecture on the concepts behind using calculus to help us graph any type of function that we're given. And I'm just going to approach this conceptually here. I just want to talk about kind of what we need to do. So I'm going to draw in a random graph here of a function. I'm not going to tell you what the function is because it doesn't really matter for this because we're just talking about the concepts and what we're going to do to graph this normally. So I've just created a very complicated looking piecewise defined function graph with two vertical asymptotes and two horizontal asymptotes. And I've also darkened in a lot of little points in here. Everything that I've darkened in black you could find using old school algebra. And let me just kind of draw in here that the blue is the x-axis and the y are the x-axis and the y-axis, I should say. And then the red is the function itself. The gray lines are the horizontal and vertical asymptotes. Now, illustrating this using a graph, normally you wouldn't be given a graph, you would be asked to graph a given function, but this is actually a little bit better to understand why we could use calculus to graph something like this, or as exactly as we can, because you start with algebra, finding the x and y intercepts and little things like that, and eventually you get to calculus talking about where your functions increasing and decreasing and stuff like that. So let's actually go through this and just mention the things that you can find using algebra and then the things you can find using your brand new calculus. And what this should do is this should allow us a better understanding of how to use calculus to graph a function. So imagine that somebody gave us a function, explicitly gave us a function and asked us a graph, and this ended up being our graph. How did we get this graph? The first thing I'll consider is the domain. So given a function, using some old school algebra, I can state the domain of that function, and that just helps me realize where I need to worry about finding derivatives and not finding derivatives, and where I can find asymptotes and whatnot. So specifically it helps me find vertical asymptotes if it's like a rational function or something like that, or if I'm dividing by 0 at some point. It just allows me to find vertical asymptotes a little bit easier. This is the first thing I look for, and then I also look for intercepts. And of course, you should know at this point how to find the intercepts of a given function. You just let x equal 0 to find the y-intercept, and you let y equal 0 to find the x-intercepts. Although in calculus, finding the x and y-intercepts, or at least the x-intercepts, can be somewhat challenging. So just as a piece of advice, that if it's very difficult to find the x-intercepts, it's usually pretty allowable to skip that part. But only if it's incredibly difficult to find the x-intercepts. Often you can find them, but sometimes it's just analytically impossible to find them. You'd have to use a graphing calculator, which defeats the purpose. Okay, so once I have to reach for a calculator to find the x-intercepts, I don't even bother. I just kind of say, analytically, I can't find them, but hopefully you can. Next thing I look for is symmetry. I'll go ahead and write that in here. So this is a step that you're looking to see if your function's even, odd. So again, you've been given a function and you're going to just determine, is it an even function? Is it an odd function? That may help you graph. For example, if this was an even function, then I'd only graph the right-hand side, in other words, when x is greater than or equal to 0, and then I would just make the mirror image of it to graph the left-hand side. If it was an odd function, again, I'd graph the right-hand side, and then I'd rotate it 180 degrees to get what the left-hand side was of the y-axis is equal to. So that's the power of using symmetry. And also there is also translational symmetry, which is if you have a periodic function. And that usually occurs if you have like trig functions involved, that type of thing. Okay? Next thing I look for, again, a little bit of algebra. This is kind of the change from algebra into calculus. So I'll put a little 4 sub 1 here. 4 sub 1 is I look for asymptotes. Now, I can use algebra if it's going to be a rational function. So if somebody handed me a rational function, a ratio of polynomials, I'll go ahead and be able to find the horizontal and vertical asymptotes that way. Otherwise, if they didn't give me a rational function, I'll likely have to resort to calculus. So finding the asymptotes via calculus. And these are done by taking the limit as x approaches positive infinity and as x approaches negative infinity. And that would be yield the horizontal asymptotes. It might yield actually oblique asymptotes if these limits are infinite, which is kind of a bigger topic. So, I'll talk about that in a future video. But for right now, we're just covering the basic idea, right? You let x go to infinity, and maybe, like in this case, as x goes to infinity, it looks as though my outputs, my y values, approach negative 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 9. Y equals a negative 9. And then that's as x goes to positive infinity. As x goes to negative infinity, the y values approach 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So y equals 10. And that's done using limits if it's not a rational function. Okay. On the other hand, the vertical asymptotes, you'll discover those as x approaches these points where your function is undefined, where you're causing division by zero, or maybe you take the natural log of something near to zero, that type of thing. Basically, where you have traditional asymptotes. So in this case, we have a vertical asymptote at x equals 3, and another vertical asymptote at x equals negative 12, it looks to be. And so what you do to find out the behavior of your function around those asymptotes is you take limits. So let me write that down again for calculus. So for vertical asymptotes, we just investigate the limit as x approaches that asymptote from the left and from the right. So in this case, for our function, I would take the limit as x approaches negative 12 from below and then negative 12 from above and see what that behavior is. If it goes off to negative infinity, like in this case, it looks to be going off to negative infinity in both cases. This is actually giving us the shape of the graph. If those steps that we've just listed out give us these gray lines, the vertical asymptotes, the horizontal asymptotes, it also allows us to plot these black points here, the x-intercepts and the y-intercept. So that's what we would have thus far. We also need to figure out kind of the maximums and minimums and inflection points. So that starts getting us really deep into calculus. And that first derivative gives us a lot of information about a function. We just check for the critical numbers and we use those to build a sign chart, right? And you find out basically where the derivative is positive, you have an interval of increase. Where the derivative is negative, you have an interval of decrease. And if you're increasing and then decreasing, you have a local max. If you're decreasing then increasing, you have a local minimum, right? So these are the things you're kind of looking for when you're trying to graph a function. Remember, the stuff in red we would not have. We would just have the stuff in black and then the gray line so far. But when you take the derivative, the first derivative, and you set it equal to 0 to find the critical numbers and also find out when the derivative itself is undefined, you can then determine the stuff. I actually will use a different color. Maybe I'll use something that's really bright, like not bright but big. Like I'll be able to determine that's a local maximum. I'll also be able to determine just from that information that we have an interval of decrease all the way up to x equals negative 12. We have an interval of increase between x equals negative 12 and where we found our maximum point. We'll have an interval of decrease beyond there. All right. So basically, your derivative just allows you to find these intervals of increase and decrease. Remember, we still don't have anything in red, but now we have everything in black and that green dot and also the gray lines. Finally, we can jump into finding the double derivative, and you set that equal to 0 and you can find the inflection points and also state the concavity. If the double derivative is positive, it's concave up. If it's negative, it's concave down. And again, remember, as I scroll up here, we still don't have the red curve, but what's really cool about this is that now, and maybe I'll write this in blue, we have the inflection points, which are where we change from concave down to concave up. So I can plot this and find out its height. We have this other inflection point where we go from concave up to concave down. So I can plot that and find its height. We have this other inflection point where we go from being concave down to concave up. So I can plot that and find its height. Let's see. Technically, this would be an inflection point as well. So we would go from concave. So I'd probably plot that in there. We go from concave up to concave down at that point. And then let's see. We have another. We're all concave up on this region until we get to here. And we're concave down. Again, this is just by setting the second derivative equal to 0, you would find these points. We would still not have the red curve. We just have these dots that I'm plotting. And finally, we are concave down. All of a sudden, it switches right here to concave up. And so we know that. And then I also, obviously, as I was saying that, know where I'm concave down and where I'm concave up. So we know that's concave down, that it's concave down here. From here to here, it looks like we're concave up. From there to here, we're concave down. Then we're concave up. And then we're concave down, right? And we're concave up. All the way to there where we're concave down. And then we're concave up. Now, everything I have plotted is known values just from finding the derivative and stuff like that. Now I went ahead and erased the function because honestly we would not have the function at this point, and I would just use the information that I calculated, and I tend to like to work from left to right. So we would have calculated that our horizontal asymptote as we go to negative infinity would have been y equals 10. So we're approaching that value of y equals 10. We know it's decreasing from negative infinity all the way to negative 12, so I know this is going to be falling. I also happen to know it's concave down in that interval, so I know that it's got this bowing down business, and I also see that I have an x-intercept that I'm going to go through. So that could only happen if I have something like this, right? This is still concave down. This is a vertical asymptote, so and we would have calculated from our math there, from our limits, that as x approaches negative 12 from below, we would have gone to negative infinity. Then as I hop over, I say, okay, well, as x approaches negative 12 from above, our y values are also approaching negative infinity. Okay, that's from our computations that we would have worked on. We know it's concave down between negative 12 and whatever this x value is that I wasn't really too concerned with finding. And I know that it's going to climb all the way up, because it's increasing, all the way up to this point which we have, and that will be an inflection point. So I know that it's concave down all the way through here. And at that point, that's an inflection point, so it's starting to go concave up in this region, and it's still increasing, and it's got to hit that x-intercept. So I've just changed inflections right there, concavity. Now that I'm concave up, and I'll be concave up for a little while longer, all the way until that inflection point, and I'm still increasing. So there we are, we're still concave up. Okay. And now I'm starting to go concave down, and I'm still increasing all the way up to that local maximum. Okay, that's a local maximum, which means that I start falling at that point. And actually, as you read above, it does say I start decreasing there, and I'm still concave down, so I start going concave down here, or continue my concave down, until I hit that next inflection point, and I plotted that. So we're still concave down, we're still decreasing. We're decreasing until we get to the y-axis at least. But now is where I switch and I start going concave up. And now if I don't see any x-intercepts, I'm kind of troubled here. I think, oh man, what's going on? But I also know that as the limit, as x approaches 0 from below, is going to be 0. So this was some type of part of my function. I have this domain issue here, and I have a limit going there, and we're concave up. So I know it's going to look something like this. It's kind of a weird function, honestly. And then I hop over 0 and I say, okay, well then I know the function evaluated at 0. For some reason I found out it was -3, and it's continuous. And let's see, it's decreasing and it's concave down. So it's decreasing and it's concave down, looks something like this. And I happen to have calculated that as x approaches 3 from below, the function's going to negative infinity. That's just my assumption that we calculated that. So this is all concave down. It's going to negative infinity. And then I do some computations. on the other side here. And let's pretend that when we took the limit as x approaches 3 from above, the function values were going off to positive infinity. Okay, and so now it says it's decreasing here, but it's concave up, and it's going to be concave up all the way until this inflection point right there. So I'm going to erase that for a moment so I can go concave up all the way down. It's going to approach this x-intercept, so all the way down is concave up here. Not my best graphing job in the world, but that's not the best at all. Let's try to get this going properly here. It's all concave up, concave up, concave up. It goes through this x-intercept. It's still concave up, but I know it's got to go through this blue point here, and that's where it's going to switch to concave down. So, boom. I'll just change my concavity at that point. It's not derivative of 0 there, so I didn't really flatten out, just changes directions. And let's see, it's concave down until this point right here where it switches to go concave up. So let me just kind of do this. And this will switch to concave up. And then as x goes off to positive infinity, our function values approach -9, so it's all concave up, and we'll approach a height of -9 as x goes to positive infinity. There we go. And that's how you use calculus, really, and algebra, a mixture of the two, to graph a function. If you go back to the beginning of the video, this is basically the function we originally had. So that's the idea behind it. Now, obviously, I didn't give you a function here. I just kind of gave you a graph initially and said this is how we're going to use calculus. But that's the idea behind it. So in our future videos, I'll just go ahead and graph a ton of these. By the way, I redid this video because within the first 6 views I had a dislike. So I decided, you know what, I'll take a different approach to this and approach this from just a graphical perspective rather than a list perspective.